Okay, so half-life. Okay, half-life. So remember half-life, right? We're talking about radioactive compounds, I guess, radioactive elements that they're constantly getting off energy, and as they're getting off energy, they are changing, their composition, I guess, and becoming a different kind of thing. And so, as they radiate away that energy, the amount of that radioactive material is going to be decreasing because it's constantly getting off that energy. And so we talk about the half-life, or the amount of time it takes for the original quantity to be cut in half. Okay, amount of the original quantity that it takes to be then cut in half. The time it takes for that. That's called the half-life. And so the formula we have to kind of like do calculations with half-life, and you'll see variations of this, depending on your class, but they're all going to be same kind of format. Okay, and this is like one of the formulations of the half-life equation. Okay, you have A, which is going to be like your current or final amount. Okay, A sub 0 or A naught, sometimes called as well, and that's the initial amount. 1/2 because we're taking half of the amount. T is going to represent the time in years, and then H is the half-life of this particular item in years. So I'll write that up here. So A, right, is the final amount. A sub 0 is the initial amount. Okay. And by the way, too, anytime... this is probably regarding attendance. So. Hello? Hi. Just to check the Google Classroom. That's all she needs. Bye. Okay. Sorry. Anytime you see a variable, or most of the time you see a variable that has a 0 as like a sub there, that means it's supposed to be like an initial amount, initial quantity of that variable. So for example, if you do physics right, and you see like a v sub 0, that means initial velocity, or a sub 0, initial acceleration, or p or s sub 0, that would be your initial position. All right, that sub 0 kind of is used to indicate an initial or a starting amount of something. Okay, so again, T is time in years, and then H is the half-life in years. Okay. All right. So here we have a made-up element, made-up item, wittium. The half-life of wittium is 40 years. If you have 6,000 grams now, how much will you have left after 80 years? Okay, and this one we can actually do mentally, right? So that's 6,000 grams. After 40 years, how many grams will be left? 3,000, right? Okay, because we've taken that 6,000 grams. 40 years later, there's going to be half that much, so 3,000 grams. And then 40 years later from that, which will now be a total of 80 years, how much will be left from then? 1,500. So the final answer here is 1,500. It's just half of the original 6,000 amount, because we're doing two 40-year intervals here to make that total of 80 years. So it's half of 6,000, so it's really just 1,500. Okay, grams. So we kind of know the answer from this one. It's like there for us to do, right? It's not necessary for us to use the formula, but let's just use the formula just to check to make sure that it does do what it's supposed to do. So we're going to find our final amount here with our initial amount of 6,000 times 1/2 to the, okay, so time in years, well in this case the time that we're talking about is 80, over though the half-life, which is 40. So there's our setup, right? The initial amount, A sub 0, 6,000, times 1/2 to the number of years that it's going to be decaying over then the half-life of 40 years, the constant half-life of 40 years. Okay. And so then the 80 over the 40, that's going to simplify to 2. 1/2 squared, well, that's just 1/2 times 1/2 times 6,000, which is exactly what we had before. So you can see it's going to be the exact same thing here. It's just going to be 1/2 times 1/2 times 6,000, which is what we have there. And so sure enough, it will be 1,500 grams as well. Okay. Okay, so let's try the 135 here as well. So now this one, right? It's not an exact number of 40s, right? We can't just say, okay, well it's like two 40-year half-lives. This is like it was an 80. 135. It's not a a multiple of 40. So we have to actually calculate this one out. So it'll be again, 6,000 times 1/2 to the 135 over 40. It's a matter of typing that into your calculator, right? 6,000 times 1/2 to the 135 over 40. Type that in, you should get 578, we'll say 0.329 grams. Okay. Go ahead and try letter C. Go ahead and try letter C then. 400. 400. Give that one a shot. Okay. We won't move on to the population problems one there at the bottom, because you guys are kind of doing that already with your population project. So we won't worry about those at the bottom there. What'd you get?
I'm not sure if I did it right, but I got it.
Yes, so it's one.
This is plain beforehand. Gotcha. Okay.
Yeah, but I got a really small number.
Okay. How small?
Like,
Like times 10 to the negative small. If I'm thinking of the negative.
it has the E and then there's the negative.
Solid. Okay. So let's check your setup then. Okay. So how'd you set it up?
I did 400 divided by 43.
Okay. So yeah. Okay. So that was your exponent. You're saying. Yes.
Oh, that's, never mind.
Ha! There it is. Okay. So it should be our exponent, right? Because the time in years is 400 years. The half-life is 40, so that's the t over h. That's the exponent for the 1/2. And we have the 6,000 out front. You got an actual answer now?
Yeah, I got 5.859.
Yeah, that's right. approximately 5.859. Of course, we don't need to use the formula here either, right? Because 400 years is just 10 of those 40-year intervals. And so it's just going to be 6,000 times 1 half, 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 10 times, right? It's just going to have itself 10 times. Okay. Also be that 5.859, which you can kind of see here. 400 over 40 is 10, so 1 half to the 10, then times 6,000. So just multiply it over and over and over again. Okay? So not even necessary to use the equation there either. But if you did, that's okay, because that's what it's there for. Questions on half-life? Okay. Okay, so I have two other problems I want us to look at in regards to what I wanted to show you guys today, just kind of covering our bases. Actually, maybe is it 2 or is it 3? Well, 2 different scenarios, I guess, but really 3 problems, I guess we'll say. I also wanted to look at some applications of logarithms. So we saw like exponential word problems. I also want to do like a logarithmic word problem, and for whatever reason, these are like really wordy. So I apologize for that. We're gonna write one out, and then we're just gonna steal one from the book as well. Okay, so we're gonna write one of these out, and then we'll steal one from the book. Okay, 2 kind of like applications of a logarithmic scenario. So the first application has to do with measuring earthquake magnitude. And so, does anyone know what the name of the scale is that measures earthquake magnitude? The Richter scale. That's right, the Richter scale. Okay, so the Richter scale measures the magnitude R of an earthquake of intensity I using, and then this formula here. So the Richter scale is equal to the log of I over I sub 0. Okay, so again, there's that sub 0 I told you about, so we know already that's like an initial quantity or a starting quantity or something like that. Okay, where in this case I sub 0 is equal to 1, where I sub 0 equal 1 is the minimum intensity used for comparison. Okay. So I feel like I think that kind of means like it's the base level of intensity. Okay, we have sort of geological activity that's happening all the time. We don't really feel it, right, because it's not that powerful. So we just call that 1. Okay, we're kind of like at a 1. It's not really out of the ordinary. It's just kind of a normal geological activity that we don't really experience, but we can measure it still using seismographs, I think is what they use. Anyway, so that's 1. But then we compare, of course, that with the intensity of when an actual earthquake happens. So we're going to find the intensity, okay, I, for each situation, or for each earthquake given below. And just as a side note here, intensity is a measure of wave energy. Of an earthquake. is the measure of wave energy of earthquakes. We compare the two intensities. We compare the kind of baseline intensity of 1 with then the intensity during the earthquake, and we take the log of that quotient, and that puts it on the Richter scale somewhere, gives us that Richter scale score. Okay, so we're going to look at one from Nevada. So in Nevada, in 2008, okay, there was an earthquake that was on the Richter scale of a 6.0. 6.0. And so we want to then figure out what is the intensity, what was the intensity scale or score for that. So that goes in for the R there. So we'll say 6.0 equals log of I, the intensity we want to solve for, over 1, the baseline intensity there. So I over 1. Okay. So what was the intensity? The wave energy. See, what was the wave energy of that earthquake in Nevada in 2008 if the Richter scale score was 6.0? Okay. So then to solve from this point, what do we do? How can we get that I kind of outside of that logarithm? What can we do? We have the I inside the logarithm. How can we cancel out that logarithm to get just into the I? Tyler, what do you want to say? Yes. So take each side, the left-hand side and the right-hand side, and do 10 to the power of the left-hand side equals 10 to the power of the right-hand side. Remember, a log by itself, without a base written, we assume that's log base 10. So 10 to the 6.0. Okay, well, I don't know why I did that on the calculator. That's silly. It's a million. Okay, and then 10 to the log is just equal to I. So in this case, the wave energy, the intensity of the wave energy is 1 million. And I don't have units for that. Let me see if I do. I might be kind of curious here. No units given. And then I'll have you guys here, let me have you guys try number 2. So let's do one, I have another one, I think, from China. Yes. Eastern Sichuan, China. And we'll say that was a Richter scale of 7.9. Okay? So it's 1.9 points higher on the Richter scale. Then we'll go see what that means for the intensity. So go ahead, find out what the I would be for that one. Okay, again, using the baseline I sub 0 of 1, right? I sub 0 of 1. Go ahead and find what that intensity would be. Kind of interesting here, right? We start with a Richter scale of 6.0. The intensity is 1 million. We start with, we go up 1.9 points on the Richter scale, so only increasing by 1.9 points on the Richter scale. But then the intensity goes up to 79.4 million. We'll say 79.4 million. Okay, 79.4 million. So it's really 79,432,000, so on and so forth. I do in the back corner there. So what that means is, right, so what's really happening here, so the Richter scale is more than just saying, okay, if you're going from a 6.0 to a 7.9, going up only 1.9, well, that's really like the intensity of the earthquake is almost 100 times as much, okay? So in this case, it's 79 times as much, right? 1 million to 79 million is about 79 times as strong, okay? So what that really means is on the Richter scale, every time you go up by 1 point, you're going up by a power of 10 more intensity. So the difference between an earthquake that's at a 6.0 and an earthquake that's at a 7.0, the 7.0 is 10 times more intense than the 6.0, and so on to the 8.0, the 9.0, and all that stuff. I don't know that's the highest one we have, but it gets up orders of 10. It's 10 times as strong, not just 1.9 more. So it's pretty significant. Okay, and so there's actually a similar relationship to when it comes to decibels as well, which is a measurement for how the loudness of something. So there's the Richter scale, but we can also talk about the decibels as well. So this is in the book. So if you want to pull your book out, I'm going to be on page 266, or you can just follow along here. I'm going to project it as well. So it's up to you. Okay. But let's see if I can get this to work. Yeah. Okay. So sound intensity, right? Decibels, that's how loud something is. The level of sound beta in decibels with an intensity of I is given by beta equals 10 times log of I over I sub 0. So it's very interesting. We measure earthquakes using a very similar formula to the way we measure decibels, which I'm wondering, they're both measuring waves, so I'm guessing there's some sort of relationship there between, sound waves and also then waves in the earth as well. There's probably some sort of relationship there. But anyway, it's a very similar measurement style. So where I sub 0 is an intensity of 10 to the negative 12 watt per square meter. Okay, that's kind of our baseline. I sub 0 is like the baseline, or the baseline intensity, which is basically, roughly, like it says, the faintest sound that can be heard by the human ear. In exercise 65 and 66, then we're going to find the level of sound theta. Okay, so you can see here we have some scenarios. Okay, so like a quiet room would have an intensity of 10 to the negative 10 watt per square meter. Okay, whereas a busy street corner would have 10 to the negative 5. Still a small number, right? 10 to the negative 5, but it's less small than a quiet room, right? So it makes sense. That's going to be like a louder area, right? A quiet radio will still be louder than a quiet room, and then you got the threshold of pain. Okay, so I guess when it's just 10 to the 0 like that, so 1 watt per square meter, that's going to start hurt your ears. They're going to start hurting your ears. But anyway, so let's measure the decibel level of a quiet room. Okay, so of course a quiet room still has noise going on, right? We have the fans going. The fluorescent lights even make like a buzzing noise if you listen. You're in a quiet enough room and there's not other stuff going on. They make like a small quiet buzzing noise. So it's not a quiet room's not so silent. Okay. So anyway, they actually have these. I don't know if you guys have ever seen these videos about these. They have these chambers that are called anechoic or whatever, where they reduce the amount of sound to nearly 0, and so people can't stay in them for long. They're able to stay in for an hour, tops maybe, and that's all they can stand because they drive themselves crazy, not being able to hear things. It's really weird. I don't know. So there's videos and stuff like that. You can check it out. But there's a couple of these chambers, and some interesting stuff. Anywho. Kind of sounds like a horror movie. But anyway, so we have, 10 to the negative 10th there is the intensity. And so our formula, right, is beta equals 10 times log of I over I naught, or I sub 0. Okay. In this case, right, I sub 0 is not 1. That's not our baseline here. Our baseline was given to us as 10 to the negative 12. And then I, in this case, well, it's the quiet room, so it's 10 to the negative 10th. Okay. And so when we, actually, this is something we can just go ahead and straight up type into our calculators, right? So 10 log of 10 to the negative 10th divided by 10 to the negative 12. Okay. And we get 20 decibels, okay, which we shouldn't really be surprised by, because 10 to the negative 10th divided by 10 to the negative 12 is, well, that's 10 to the second, it's 100. And log base 10 of 100 is going to be 2. 2 times 10 is going to be 20. So that one we can actually do mentally there too. But we'd say 10 decibels. Okay. Or sorry, 10 decibels. 20 decibels. Sorry, the final answer there. Okay. So go ahead and try B. Find what the decibels would be on a busy street corner. Okay. Hopefully, we think it's going to be more decibels, right? So go ahead and do that calculation here real quick. And then we'll be done. So, Carolyn, what'd you come up with there for letter B? 70, yeah, 70 decibels. So again, here, another kind of interesting scenario, right? When we talked about the Richter scale, going up 1 point on the Richter scale really resulted in going 10 times stronger, right, for the intensity of that earthquake. Here, we went up 50 decibels, okay, so going up 50 decibels is equivalent to taking something that was at 10 to the negative 10 and to 10 times, or going up to 10 to the negative 5th. So that's, 10 to the 5th, times greater, I guess. Okay. So every time you go up, every time you go up 10 decibels, it's 10 times as loud, I guess, is what we could say there. 10 times as loud. So going up, 50 decibels is much louder. 100,000 times louder. So, very interesting. Okay. So, okay. Very good. So, there's that. All right, and that's kind of it. Okay, we've covered everything now, and we're good to go. So, we can get to work now on, if you want, on your review sheet. And I'll post the answer key to that online right now. And then also, you can work on your population project if you so choose. You can work on that some more. You can ask me questions and things. And then, yeah, I don't have... Oh, I do have a few homework problems I'm going to assign, yes. So I'm going to give you guys a couple homework problems as well. So.